All right, good morning, everybody. Not the class, it's a rather wet morning later. So today I want to start the next section, essentially, and I want to talk about integral transforms. So some of these integral transforms you will have seen before, I hope. They should be quite familiar to you, and I'm going to start with the most familiar of the transforms. Okay? The Fourier transform is what I hope to cover some of today. I'll also talk about some commonly used transforms. So we're going to focus on one or two of these things. And I'm going to focus on it in a particular way that you may not have seen. So you may have seen these transforms before, but probably haven't seen this way of thinking about it. The point is, there's a common way of thinking about integral transforms that gear up towards integral representations. This is where I want to go with this. Okay? So I'm not interested in Fourier transforms, and particularly as a means of solving differential equations, which they are very good for. I'm interested in it as a way to generate integral representations or solutions to differential equations. But I want to start off today by just finishing up the last section, which was the double periodicity of elliptic functions. Right? So we said that the elliptic functions are generalization of trigonometric functions. Trigonometric functions were periodic in one direction, either the real or the imaginary. Doesn't really matter, you can always rotate the axes. But the point is, they're periodic in one direction. My claim was that elliptic functions are periodic in two directions, so both in the real and in the imaginary direction. Okay. I gave you an argument last time for what it means for a function to be periodic. And I said that use the periodicity of a function. We use the example of sine x. Not by actually having an explicit realization of the function, but some representation. Okay. So in our case, we know that the sine function is a unique solution of a differential equation subject to some bounding. Right? Essentially, the harmonic differential equation subject to the bounding condition that y belongs to 1. And we use this to deduce the periodicity property of the solution, not really knowing that it was a sine function. Right? And then the reason we did this was we wanted to benchmark our intuition. We want to solve the problem that we already know the answer to and understand how the mechanics of the solution works. And that's what we do. But it's not exactly the same argument with the elliptic functions, knowing that there are solutions of differential equations, which I've written down before. So, for example, the harmonic, that's the pendulum equation, not the pendulum equation in the harmonic approximation, but just a full pendulum equation. Well, this is a solution. Okay. And we can use that fact together with the boundary conditions of the differential equation to run exactly the same argument that I just did. When you do that, you will find the following. So I'm just going to write down the periodicity properties of these functions, and then I'm going to give you a physical argument as to why it should be doubly periodic, going back to the pendulum. So you can show that the Sn function, Sn of z plus 4k, and I'll tell you what k is just now. Okay, that is. It is the same as Sn of z k and Sn of z plus 2 by k prime and k is k, capital K, is some real number defined to the integral from 0 to 1 of dy over the square root of 1 minus y squared 1 minus k squared y squared. And k prime is the integral from 0 to 1 over k of similar square root y squared minus 1 times k squared y squared integrated with respect to y. And the key point here is that both of these things are real numbers. Which means that what's happening here is that if I shift z by some real number, right, that real number, then I get back to the elliptic sine function. Similarly, if I shift it by 2I times that real number, so this is a shift in the imaginary direction, then I get back to the elliptic sine function. Right? So this demonstrates that, and you can check this explicitly, this demonstrates that so one more constraint is that the modulus must be between 0 and 1. Okay. This demonstrates explicitly then that these functions are doubly periodic. They're both periodic. This is an and, not an or. They're both periodic in the real direction as well as the imaginary direction. Okay. But let me see if I can do a more physical argument for why this must be the case. So let's go back to the pendulum. Let's note the following two facts. The first one is that given the physical problem of the pendulum, and again, I'm not restricting myself to any particular range of angle, right? But I know that if I start the pendulum off somewhere and I let it oscillate, then there's some time later t in which the pendulum returns to its original position. Okay. So, for example, if I started off here, there was an oscillator and it comes back here, that's the original position. Okay. So there's some number t for which theta of little t plus capital T is the same as theta of t, where theta is the angle. Okay. So for some number t, which in our case is 4k. Okay. This necessarily implies that the variable x, the rescaled variable x of t that we just defined, is also periodic. And you remember that the solution that we came up with was that x was the inverse elliptic sine function. So if x is periodic, the left hand side is periodic for period t, and the right hand side has to be periodic for period t as well. It means not necessarily that so it is Sn of z plus t K equal to Sn of Z. Okay. So this much is clear because I know that the angular variable that defines the pendulum is a periodic variable. Okay, so this was an obvious statement. The second statement is less obvious. The second statement, we want to show this, in other words, periodicity in the imaginary direction. So to that end, let's analytically continue the time variable to I times the time variable. In the physics literature, this is called a Wick rotation. Right? So if we analytically continue or equivalently Wick rotates, those of you who are doing physics, you may have seen this before already. This is a Wick rotation. And it's defined by sending T right. Okay, that's all. It's just make a 90-degree rotation of the time axis. But I want to do this in the defining equation for Newton's second law. Right, so Newton's second law says that the force applied to a system is proportional to the acceleration so if I make an analytic continuation of t to I t, there are two factors of t sitting in the denominator that give me -1, right? Which I can take to the other side. So this says that in this new system, just like my old system, except force applied in the opposite direction. So the effect of the analytic configuration, Wick rotation, whatever you call it, is to reverse the direction of the force. Notice that direction of F is reversed with a Wick rotation. And in our pendulum problem, this would mean that we reverse the sign of gravity. So we invert the pendulum. Okay? So gravity, so this necessarily implies that in our Wick rotated system, gravity acts upwards. So where gravity acts downwards and pulls the pendulum downwards in the normal pendulum, this Wick rotated system where we've rotated by 90 degrees the time axis, gravity acts to pull the pendulum upwards. So if I displace the pendulum from its perfectly vertical upward position, it will rotate about that upward. But even an upside down pendulum is still a pendulum. So it satisfies all the physics that we come to expect of the pendulum. What that means is that an upside down pendulum is still a pendulum. Means that this elliptic sine function is still a solution of the pendulum equation. which must still satisfy the properties of solutions of the equation in this periodicity problem. Except we can quick rotate it time variable. So really what we're saying here is that the elliptic sine function plus some periodicity variable t, let's say modulus k, is Sn by t. Okay, with this guy here, t tilde is 2 by k prime. So together, these results mean that as a function of some z in the complex plane, this elliptic function that is the solution of the pendulum equations must be periodic, both in the real direction as well as in the imaginary. Okay. So again, I haven't done a bunch of math here. This is a physical argument, but just looking at the pendulum, changing the sign of gravity, and noting that it must still be a pendulum, it demonstrated that the elliptic sine function has to be periodic in both the real direction and the imaginary direction, which establishes what we set out to do, which was to demonstrate or find a function that was doubly periodic. Okay. So for the next section, the next section, I want to talk about the idea of integral transforms. First, any questions about both of this? Online, anything?
Nothing else.
Nothing. All right. So now I want to broach a really important subject. And this is the idea that functions in mathematical physics often come in pairs. Sometimes you call these Fourier pairs, sometimes you call them class pairs. The point is that one function is related to another function through an integral. Right? It's one function, an integral for and these relationships persist over a span of mathematical physics. If you want something anchored to, think about Green's functions. Okay? If you have a differential equation, you would like to solve that differential equation. One way to do it is through the method of Green's functions. The method of Green's functions tells you to take the initial condition system and convolute it with, sorry, the initial condition. To take the source term of the equation, the right-hand side of the equation, and convolve it with a function that is inherent to the system itself, the Green's function. Okay, the Green's function for a particular differential equation is the Green's function. I can change the right-hand side, the inhomogeneity of the differential equation as much as I want. Okay, but the Green's function remains the same. It is the response function of that system. Once you know the Green's function for a particular differential operator, that's the Green's function for that operator. You will find the solution of that differential equation subject to any right-hand side, any inhomogeneity. You just multiply the Green's function by that source term and integrate. Right? And the answer is the solution of the differential equation. So the solution of the differential equation is one function. The right-hand side, the source term, is another function. And these two functions are related by the integral. And what's common to all of those types of solutions are the boundary conditions of the integral and the Green's function. So there are many functions in mathematical physics that are related to other functions through expressions of the following form. Okay. So these two functions are related, f and g, and they're related to an integral like this. So the integral takes this function f of t to the function g of x. Okay. This guy here, k of xt, is called the kernel of the transform. And it's understood that as long as we're talking about this particular transform, the kernel, k of xt, and the limits a and b are the same for all function pairs f and t. Okay? So I specify for you what this kernel is and what a and b are, what the problem specifies this for you. And then given some f, you calculate t. Okay? So this should be compared to, for example, what you know from method of Green's. Compare this to the Green's function solution of an homogeneous differential equation. So very often it will help to define this integral relation symbolically. And the way we do that is to say that this g of x is the transform of x on s. This is an operator notation, but same thing. This here is called the integral transform operator, and it depends on a, b, and kernel a of x. So I specify for you what the boundary condition, what the limits of the integrals are, and the kernel of the transform that defines a particular transform, and symbolically I say that the transform operator acts on f of x to produce g of x. Tx is a linear operator. Because integrals are linear operations. In other words, the integral from a to b of f1 of t plus f2 of t k of x and t dt is the integral from a to b f1 of tk x t dt plus integral from a to b f2 of t k of x t dt, where this guy is the action of k on f1 plus f2. This is t on f1 plus t on f2. Similarly, again, because of the way integrals work, the integral from a to b of some constant at f of t a of x t t constant at the integral from b of f t k of x t t. In other words, t acting on c of x is c times t acting on x, whereas c is some constant. Okay. None of this is particularly deep. Everything you understand about integrals applies to the integral transform. So, in order for an integral transform to be useful, we need to be able to undo what t does. In other words, there needs to be an inverse that is relatively easily computable. T. Okay. When this is possible, we can invert. So if T inverse exists, then f of x is T inverse of x. It's not always the case that the inverse exists. It depends really on the integral transform itself, which by extension means that it depends on the kernel of the integral transform. Okay. And even if it does exist, it's not always true that it's easy to invert, easy to compute. And the reason we want to do this is because the properties of integral transforms very often lend themselves to making our lives easy, getting the problem. So, as an example that you may be familiar with, Laplace transforms. Laplace transforms have one very big advantage in that because of the structure of the transform, they take differential equations to algebraic equations. If I give you a differential equation, x space, say, or t space, let's say, and you integral transform this with a Laplace transform, you'll get to Laplace space, s space, say. And in s space, this differential equation, t, becomes an algebraic equation in s. And you can solve the algebraic equation in trivially. Right? As long as you know how to invert the operator, you have the solution already in t space. But there's the problem. Problem is that inverting the Laplace transform in general is a notoriously difficult task. This is why they kind of don't teach it to you in undergraduate courses that you have done. That you may have seen Laplace transforms. Yeah. Engineers have this algorithm for how to use. So, Laplace transforms are very often used in engineering applications. Constantly just take the Laplace transform of various different equations, simplicity, circuit theory, etc. And there, you just do lots and lots of examples, and it tells you all the forward transforms. And you use the forward transforms together with some of the properties of the integral transform to invert them, essentially using a table of transforms. We don't want to do that. We want to be able to invert them generally operate. Okay. And for that, the Laplace transform is a very difficult transform too. Well, not very difficult, but it's more difficult than Fourier transforms. Okay. But the general philosophy of why we want to work with integral transforms is really twofold. One is, like I said, with the Laplace transform, more often than not, the transform function g of x is much simpler to work with than the original function f of x. Okay. It satisfies different properties that are often much simpler than the original properties satisfied by the differential to algebraic equation relation is one of them, that's something else. Okay. The second thing is that such integral transforms are highly useful if you want to generate integral representations of known functions. The one that we're really kind of building, everything we're doing towards this is the hypergeometric function. Like the hypergeometric function satisfies some second order differential equation, ordinary differential equation, which can be solved. The solution of it is the hypergeometric function. And what we would like to do is give an integral representation of the hypergeometric. Okay. And that integral representation, we're going to use integral transforms to generate. The point is that if I want to solve a differential, if I want to solve an equation involving the hypergeometric differential equation, if I want to solve the hypergeometric equation, more often than not, it's more useful to write down an integral transform and read off write down an integral representation and read off what that solution should be doing, various limits, than it is to actually write down the solution. Okay. So that's where we want to go. We want to work with transforms for two reasons. One is that G is very often simpler than S, and the other one is it's very useful for generating integral representations. But before going into the details of any one particular transform, let me enumerate some transforms that we will see very often in mathematics. And these transforms occur, everywhere from classical mechanics to field theory and sphere theory. It's not really confined to anything in particular. And as such, I don't want to focus on any one particular transform. I want to talk about what we can learn from studying a bunch of different transforms, what we can learn about transforms in general. So some common transforms that we will encounter are, for example, the Fourier transform. It's by far the most commonly encountered transform for many reasons. One is it also transforms differential equations into algebraic equations, for one. Two, it's straightforward to invert. And so the philosophy is, I give you a differential equation, you want to solve the differential equation. So you transform the differential equation to an algebraic equation. You transform the differential equation into an algebraic equation, solve the algebraic equation for whatever the transform function is, and you invert that transform function to get the solution to the original differential equation. Okay, so the Fourier transform then of S into G acts as F acting on some function G, some function little f of say T, and I'm going to write these things down in the notation that you're commonly this is the function G of omega. Okay, don't be fixated on T's and omegas and X's and P's and stuff like that. The point is, this acts on some function to produce some other function. And the definition of this is as 1 over root 2 pi, and my definition that we're going to be working with. 1 over root 2 pi, the integral from minus infinity to infinity of f of t e to the minus pi omega t. This is the function of omega. Some things to note. The kernel of the transform K of omega t, the Fourier transform is just e to the minus pi omega t. That's the kernel of the transform, and it is the thing that remains the same irrespective of what the f is. So that's what defines the Fourier transform. That and the fact that the integral limits run from minus infinity to plus infinity. Remember, I said I specify the transform by the limits of the integral as well as the integral term. The integral term minus minus t, and the limits run from minus infinity to infinity. And this factor of 1 over root 2 pi is conventional. Depending on the textbook, your paper you're reading, sometimes that factor is a 1, sometimes the factor is a 1 over 2 pi, sometimes the factor is 1 over root 2 pi. 1 over root 2 pi has the advantage that form of the Fourier transform and its inverse are the same. They both come with a factor of 1 over root 2 pi. Some textbooks, some papers use a 1 for the forward transform, which is what this is, in which case you would need a 1 over 2 pi for the inverse, and vice versa. Okay, so just keep in mind that it is just a convention. There's nothing fundamental about that factor. It's there to normalize offsetting functions. The second transform that you're likely to encounter commonly is the Laplace transform. And I'm just writing down the forward transforms now. We'll talk about the inverse transforms in general. And we'll specify these for you separately. So here, given some function f of t, the Laplace transform acts to take f of t to some new function which is conventionally, let's say, the Laplace transform conventions, capital denoted by capital, whatever the function is. In this case, f of s. So this is defined to be the integral transform that runs from 0 to infinity. Again, the limits of the integrals are what define the integral transform together with the kernel. In this case, the kernel is minus st, it's a real exponential. dt. So this is the Fourier kernel. And the Laplace kernel A of S P is e to the minus st. the thing is that, yeah, you know, you would think, well, the kernel here is a real exponential, the kernel here is a complex exponential. It might be more difficult to invert this guy than it would be this guy. Turns out not. You do a real integral to invert most Fourier transforms, but the general expression for the inverse of the Laplace transform is a complex valued integral. So you have to do an integral. If you do an integral along a line that's parallel to the imaginary axis, it's called a Roman integral. So we'll define this and work with it a little later. But the point is that you can't just do an inverse Laplace transform in general without knowing how to do complex integration. Whereas you can for the Fourier transform. The next less commonly encountered is called the Hankel transform. Hankel transform is defined as follows: given some function f of t, you do the transform of it to get some new function g of alpha. G of alpha is the Hankel transform of f t. And the f of t is defined as an integral from 0 to infinity of f of t jn of alpha t integrated with respect to t, where the kernel here, the Hankel kernel, k of alpha t is j n alpha t, where jn is the Bessel function. And finally on my list is the so-called Mellin transform. Mellin transforms are very useful in conformal field theory and partial field theory more generally, but specifically in the branch of what the field theory is called conformal field theory, where given some function f of t, the Mellin transform of f t is called g of alpha, and this g of alpha is defined to be the integral from 0 to infinity of f of t times t to the alpha minus 1 dt, where now the Mellin kernel k of alpha t is the power t to the alpha minus 1. If this transform looks familiar, that's because the gamma function, gamma of alpha, is just a Mellin function of, is just a Mellin transform of an exponential. So note that gamma function that we've talked about before is just a Mellin transform of e to the minus t. And what this means is that all of the properties of the gamma function that you're familiar with can really be thought of as properties of the Mellin transform. Okay. So what I'm hoping to convey to you here is that all of the stuff that I'm talking about that seem disparate topics. I started off talking about special functions, then we moved on and talked about elliptic functions, and now we're talking about integral transforms. They're all related. Common thread here is they're all integrals, but they're all related to each other in various ways. Okay, and I want to convey this to you. I want to show you that all of this completely disparate stuff in mathematics is all kind of related. There are many different ways you can relate these things. We could have chosen this course to focus on representation theory of leaves, for example, right? And I would have covered equally broad spectrum of topics. I'm choosing to go here the analysis route. So everything that we're doing has to do with integrals, differential equations. Okay. This is one branch of mathematical physics. It's not the only one, but I'm hoping that what you get out of this is that all of this stuff are really tied into each other. And so if you approach these topics with a broad, powerful set of tools, like these tools of analysis and representations, it'll really take you quite far in solving these physical problems. Okay, any questions? In person, online? So let's talk about Fourier transforms. Now, again, I want to stress to you that the point of what I'm saying is not to focus on Fourier transforms. It's not to focus on any particular problem we're trying to solve using Fourier transforms. It's to try and extract universal lessons about integral transforms. Okay, so things that I think are going to be common between Fourier, Laplace, Mellon, etc. I'm going to point these things out. Okay, that's what I want you to take away. So, the Fourier transform, as we've written here, really has a wide range of applications. From astronomy to chemistry to theoretical physics. Okay, you'll find it everywhere. There are many formal things that we can say about the transform, following from what I just said, but I want to try and just remind you if you've seen Fourier transforms before, and help build your intuition if you haven't seen Fourier transforms before. So we're going to do some examples, and we're going to take away the lessons from those examples. Right. So to work out some examples. See what they learn. The first example I'd like to work out is what happens if you try and Fourier transform an exponential. So let's take a look at the exponential f of x. And f of x is going to be e to the, let's say, minus alpha times the absolute value of x. And alpha is going to be some positive number. In which case, Fourier transform, which I'm going to call g of k, is 1 over the square root of 2 pi times the integral from minus infinity to infinity of e to the minus alpha mod x times my integral kernel, which is e to the minus pi k x. And I'm integrating respect to x. Right. Clearly, the integral splits up into two. One goes from minus infinity to 0, the other one goes from 0 to infinity. When x goes from minus infinity to 0, x is negative, so mod x is minus x. When x goes from 0 to infinity, x is positive, so mod x is x. So this integral splits up into two. One over root 2 pi. I'm going to go from minus infinity to 0 of e to the alpha x minus pi k x dx plus 1 over root 2 pi. I need to go from 0 to infinity e to the minus alpha x minus pi x dx. Each of those is an elementary integral because we're integrating with respect to x. Alpha minus ik is the coefficient here, minus alpha minus ik is the coefficient here. They're elementary integrals, I can do those and then evaluate them. What I will find is that this is just 1 over root 2 pi times 1 over alpha plus k of this integral and 1 over alpha minus ik of that integral. So this is 1 over alpha minus ik plus 1 over alpha plus okay, as usual. Let me check this. But I can then add these two things together, and then this tells me that this is 1 over root 2 pi times 2 alpha over alpha squared plus k squared. So that is the Fourier transform of the function e to the minus alpha times the absolute value. And I do think I want you to note about this example. These are the things that I want you to take away. One is the function that we started off with, and admittedly I'm making a broad statement with only one data point here, but you can check it on the data points. The function that I started off with is an even function. The modulus of x is an even function, so e to the alpha modulus of x is an even function. The function I ended up with is a real function. Had I not had this modulus here, had I not had this being a positive power, I would have ended up with something that was complex. Okay, again, one data point, so I really should be putting my faith in this. You're welcome to check with other functions that are not even, that the following is. The Fourier transform of an even function is real. Okay. Dude in general, you know that an even function must satisfy the property that f of x is x minus x. So take a function, an even function that satisfies f of x is f minus x, and you can show that Fourier transform is going to be real. The second universal lesson to be learned from this is the following. This function, e to the minus alpha x, looks like the following. There's x, there's e to the minus alpha mod x. When x is negative, this thing looks like e to the alpha x, so it goes up. right up until x is 0, in which case this is 1. When x is positive, it goes like this minus alpha. So the function looks like this. Okay. What happens as I increase the value of alpha? As I increase alpha, the function gets steeper and steeper. I mean, I hope you appreciate that this is symmetric. I'm just going to bear out this. Okay. So the point I want to make here is that the blue alpha is less than the red alpha is less than the white alpha. So you make the function more and more localized around the origin, the bigger you make alpha. Is that clear? Okay. What about this side? Well, this side, I've got a function that goes like alpha over alpha squared. If I divide 2 by alpha, the numerator and the denominator, I get a function that goes like 2 over alpha plus something over alpha. If I make alpha bigger, this function gets more and more delocalized. Okay. Up to the point where if I let alpha go to infinity, so if I let alpha go to infinity, this guy goes to a constant. So the more localized f is, the less localized g is. The logical extreme of this statement is what happens when I take Fourier transform of the Dirac delta function, which is the most localized function you can get, 0 everywhere, and it's infinity at the point where it has 4. Okay, so if I calculate Fourier transform of the delta function of x. This is just 1 over root 2 pi. That's the integral of minus infinity delta of x e to the minus I kx dx. This samples this thing at 0. Okay, so this is just 1 over root 2 pi, which is a constant horizontal line, arguably the most delocalized function. So again, Fourier transform of the most localized function you can get is the most delocalized function. Okay. All right, let me stop here. And we'll pick it up again on Friday, and I'll do a couple more examples, and again, see what we can learn from each of those examples of properties of the integral transform with Fourier Pairs.
We wanted to discuss the kind of stability of the
Yeah. How much time do you have? Friday? Yeah.
And general Wednesday,
Yeah.
is it before the clock starts on Wednesday?
Um,
Wednesday.